Like, so the first tutorial is continual learning beyond catastrophic forgetting in class incremental scenarios. So this tutorial will be given by Vincenzo Lomonaco, and Antonio Carta, so who are both professors at University of Pisa. So thank you.
Thank you so much, Sarah.
All right. I hope you can hear me well, also remotely. Thank you so much for being here. So it's up to me now to start the first part of this tutorial. That would be also kind of an introduction, I guess, to a larger scope of the conference. So my introduction will be about deep continual learning. So it's, let's say, another area with respect to what is the ambition of CoLLAs and learning with lifelong agents. And then the second part of the talk will be up to Antonio to see what we can do beyond, let's say, current approach and vision that we are discussing within our deep continual learning community. All right, so much of what I'm going to be discussing and the work we are doing at the University of Pisa is thanks to a larger group of people, the Pervasive AI Lab, that is working at the intersection of other interesting research areas in computer science, high-performance computing, reservoir computing, and then mostly machine learning, continual learning. So if you're interested in what we are doing at the University of Pisa, and actually if you want to visit us there, it's a pleasure for us to discuss collaborations or anything you can see connected with your interests. And final add before the start of the actual tutorial, I'm also part of this nonprofit research organization, ContinualAI, which you may know already, that is all concerned about lifelong machine learning, and is trying to provide a platform for researchers and enthusiasts to connect more, develop ideas, and also share tools, assets that we can reuse in our teaching and research endeavors. So feel free to reach out to us or visit the official website, continualai.org, if you want to learn more about the organization. All right, so in this first part of the tutorial, I'm going to go through the fundamental concepts and current focus of the methodologies, ideas that we are developing in our deep continual learning field. So maybe for some younger researchers, this part would be most useful, and especially if you're coming from, let's say, related areas like reinforcement learning or out of distribution detection and domain adaptation. But this is very much focused on what we are doing in deep continual learning. And so I will try to give the basics with that interesting twist and flavor, hopefully, so that other more expert people are not annoyed by it. That will be fundamental to attack the next part of the tutorial to see how we can improve and what we can do beyond the current, let's say, I would say, specific strict formulation we're using nowadays. And so we start with trying to describe what are the goals of lifelong learning with artificial agents. And I will try to split them in two, because you see during this talk and tutorial is, I think, interesting and useful to consider. And we'll start also with the image you should be already familiar, that you can see on the right, that is taken from the Artificial Intelligence, A Modern Approach book by Russell and Norvig, and is describing the basic agent architecture. So we are supposed to create intelligent agents that interact with a particular environment and are able to, with a utility function, some goals, maximize their expected results and act intelligently in this environment. So what we are trying to build up with CoLLAs and with these larger communities of lifelong learning agencies, rather consider those environments as not fixed, but ever-changing, or even considering access to different environments over time, and there are different environments with goals and tasks that cannot be described in a static formulation of the problem. And of course, this is also, amply, I would say, described within the book itself, but has not been the focus of AI in the last few decades, I would say, where we had, of course, different priorities to solve first. But nowadays, what we're trying to attack are those goals of incrementality. So we would like to develop, say, sustainable AI solutions that are able to autonomously build on top of what they have previously learned. So this idea of incrementally developing a better understanding of the external world, and then tackle more and more complex problems as we face them, as humans do, right? So we start playing maybe in our home garden playing soccer, then we start training on futsal or soccer 5-a-side, and then we're able to even move to professional football later on in our lives, right? And the second important goal that I like to see, let's say, different, separated from the first, is the idea of fast adaptation. So the concept that the world is changing and something that was previously there was true is not true anymore, and we need to adapt to this new circumstance, this new situation, even forgetting about the past. So we don't want to add on top what we had previously learned, but we want to forget some bias, not anymore vital or useful information. We want to adapt to what's changed in the world. So those are, I think, two different goals. And we'll see that at the moment, within deep continual learning, we're not attacking them both with, well, let's say, more comprehensive methodologies or benchmarks that we are developing. And of course, continual learning, lifelong learning is not something new in terms of vision. And even if you consider the computer machinery and intelligence paper in the 1950s by Turing itself, within that paper, Turing describes the idea of not building directly an adult brain, but moving towards like the idea of building a child brain that can learn over time as new tasks and situations are arising. And he asked himself, why should we build an adult brain if we can build something that is more autonomous and adaptive and can be personalized to the specific needs or problems that we may face. And over time, I mean, this is a non-comprehensive list of seminal papers. This idea has been developed with different methodologies and approaches, like from logic to probabilistic approaches, and even more recently with neural networks. And maybe we don't have the time to go through these, and I'm not aware of a paper with a very dense and well-crafted history of this idea of lifelong learning. But you can still read here some interesting references where this has been discussed, like the lifelong learning book from Bing Liu, that should be also speaking as a keynote speaker in this conference. And I would say the seminal continual learning dissertation from Ring in 1998, for example. And on the right, you can see a plot that is taken from this nice paper from Martin Mundt about the number of papers published each year on the topic, so selected by keywords. I guess should be normalized by the number of papers published every year. This is also growing exponentially, but it still suggests that there is a growing interest in this area and connected to what we are doing in this conference, as also the previous program chair's presentation also suggested. And so I think that in order to understand how we can build these incremental and adaptive methodologies for our lifelong learning agents, we need to understand first how the world is changing. And during the history of machine learning, computer science in general, we have been studying this phenomenon. So how we can describe the change in the world. And I also use here a quote from Ragnar Lothbrok from the TV show The Vikings, that is also saying the world is changing and we must change with it in order to face it. And as a nice also historical note, Vikings also reached Canada like about 1,000 years ago. And they had also a very long history that is very successful because they had the ability to change in a very complex, settling, I would say, environments. And so we can use, fortunately, a lot of, let's say, theories and developed concepts by other research communities, areas, like the concept drift adaptation community, which also describe, let's say, the kind of drifts and situation we may face in the real world. So a concept drift is a change in the real world and affects the input-output distribution that are important and are modeling somehow our way to understand the world. And we can notice that this is happening by disruption in terms of our predictive models performances. So if we deploy any predictive model in the real world for solving a predictive task, at some point we will notice a degradation in the performance if we don't update it. And this is most likely happening in the real world situation because the world is changing itself. And it is important to note that this is not noise or it's not outliers, but it's a real distributional change. And here on the right, you can see some types of drift that you may face. Sudden drifts, where you have this sudden change in a distribution you are modeling. Gradual, where for a moment those distributions are interleaved, then you have only the second possible distribution. And or incremental drifts, where you are moving gradually over time from one distribution to the other, or recurring concepts, where you have an interleaved situation, but you see both distributions for a very long time. And we can also try to define the kind of changes that we see in the world with a probabilistic approach, I would say. So given an input, for example, x1, x2 till xt that you see over time, and a particular concept class y, we can apply the Bayes theorem here and say that the probability of y given xt equals to the prior probability of y and times the computational probability of xt given y and normalized by probability of xt. And why should we really care about this? Well, because we can identify different causes for the change based on what's changing in this formula, what probability is changing. And we can act differently, so we can develop new methodologies based on different shifts and drifts that we realize in the world. So this is why it's important to understand what is actually changing and not consider just possible change, which you adjust to. And so we need also a bit of notation if we want to use what's being called the dataset shift notation and nomenclature, because there was an entire community working on trying to understand how learning in a particular distribution can then be used when you have a test set or different situation in the real world where you have a drift. So not necessarily understanding it in a continual fashion, where you have a continual set of data from which you have to learn from and from which your model should learn and adapt to. And so the notation here is, well, X are the input features or covariates, Y is the class or target variable, P of Y and X is the joint probability distribution, and sometimes these notation X arrow Y is intended as the relationship referred with the generic term concept. And this nomenclature I'm going to introduce is also based on the notion of causal assumptions. So we are considering two kinds of problems from X to Y, where the class label is casually determined by the input, for example, credit card fraud detection, and Y to X problems, where class label determines the input, for example, medical diagnosis in the opposite direction. So when we have fixed this nomenclature, we can use, let's say, and talk about a specific formally defined characterization of the drift that we find in the world. This community started with a very, let's say, general definition that you have a shift in your data set if there is a difference in the joint probability distribution of the training set and the test set. So you have just two different set of data. In this case, we can consider them as different tasks or experiences that you see over time in your continual learning setting. And so this is the most generic, let's say, definition of a shift. Then you can define the covariate shift, which happens in the X to Y problems we have described before, when the conditional probability of Y given X of the training set is the same as the conditional probability of Y given X of the test set, the other set we are considering. But what we have here is a different prior probability on X between the two different set of data, so training set and test set. And informally, this is when the input distribution change and the relationship from the input to the output does not. Then we have the prior probability shift where the conditional probabilities stays the same, but the prior probability for the Y target variable is different. And informally, this is again describing the situation in which you have the concept of, let's say, the relationship between output and input that is the same, but the probability of each class has changed. And finally, you have the most common, I would say, and studied concept drift, where the conditional probabilities are changing, regardless of the different causal directions, okay? And the prior probabilities are staying the same. So you see that we can already characterize non-stationarity in different ways, and this is useful later on to understand what we are doing wrong, or if we are having like another focus in what we are doing right now. And Antonio will take also this nomenclature and extend, let's say, our discussion on what we can do beyond the current formulation. And then the final piece, let's say, that of nomenclature we have to use is this difference between real and the virtual drifts. So this is also used often in learning in stationary environments and concept drift adaptation communities. And we say it is real drift when the decision boundaries in your data, for example, in a classification problem, is changing. And we say it is virtual if it is not. So if we have, in this image, I hope you can see my pointer, or you don't. Maybe there is a way here. Okay, well, I find it. But in any case, in this image on the left side, you can see the original data and our ideal, let's say, separation boundaries between these different distributions, the different set of examples related to the different classes colored in red and green. And if the decision boundary is actually changing, we say this is a real concept G. So we need to adjust in our prediction models, understanding of the world in this way, while we may see a drift, for example, probability of X, we described before, which is not changing our way of understanding the concept of those classes, and hence also the decision boundaries between the two classes. And those definitions are also connected to the specific causes of the shift. So the virtual drift are often characterized by a sample bias. So the fact that we are not able to sample our observations in a way that is representative of the entire world we would like to model, and the task, for example, we want to solve. This is very common in reinforcement learning. So if you have a single agent and you want to create a general policy to solve a task, you need to collect a lot of observations, maybe with the replicas of the same agent, or going around the environment, and then use experience replay to make sure that your policy is not biased towards the latest observations, right? So this is a clear problem with the sample bias, and the world is not changing there. The environment is static. Or we can face real non-stationary environments where the reality is changing itself. The reward maybe is changing. Now I have to grab this object because it gives me a reward. Next day, maybe the apple is rotten. I have to avoid it. I don't have to take it anymore. So the world has changed, and we need to adjust our policy to reflect that. And what I wanted to really underline in this talk is, at the moment, the deep continual learning community has been mostly focused on virtual drifts. Okay, so we assume that the world is static, and we're just not able to sample the data in an IID fashion that we know is very useful when you want to train predictive models with gradient descent. So we are focused on the first goal that I mentioned at the start of the tutorial, this knowledge accumulation rather than adaptation. But why it is interesting nevertheless, and we have been focusing on this so far? Well, because of the well-known stability plasticity dilemma in biology, where it is quite difficult to remember past concepts, what we have learned in the past, and learn new concepts are most of all generalized over time. So understand when we need to remove maybe some biased informations and let's say reformulate a better and more general concept that is able to generalize to out of distribution or unseen, let's say, data. And this is quite difficult to do with the parametric neural networks due to the problem of catastrophic forgetting. So we quickly erase all the information we acquired about the world and we have learned from the previously observed data in favor of the new data distribution, the current one we are exploring. And especially if we train those neural networks with gradient descent and standard, let's say, optimization algorithms. And here on the right, you can see an image on what's happening. So if we start with the random initialization of our models, and then we just train up to convergence to represent better those this distribution for the first task, A in green. Then if we just start from these reference vector neurons like black crosses, and we want to move to represent also the distribution of the new data, a task B. Well, if we don't impose any regularization, we don't do anything, we just continually and naively, let's say, update our model parameters towards this task, then we just move towards it and we forget, we are not able to represent anymore the previous data distribution. If we are too rigid, so we don't actually go up to convergence in, let's say, modeling this new data, we find ourselves like halfway through the process and we are not able to represent any of those distributions. So the idea of heterogenic, let's say, plasticity and any continual learning approach is instead to try to overcome this and find a new way to represent both data distributions. And this is, for those of you that have never seen this in practice, an exemplification of catastrophic forgetting, what we mean by it in deep continual learning. So if you consider this, situation where we encountered during 9 days of permanence in a specific home, that you can see also represented in the x-axis of the first plot. So we represent the ability of a predictive model to learn about new objects we see every day in this house, and we want to assess the performance, the overall capacity of the ability of this model to distinguish these 50 different domestic objects. So what we would expect is an accuracy, an overall accuracy in all these objects that would grow over time. So we encounter more objects every day, we expect our ability to distinguish them to increase. But what we can see instead is a flat accuracy curve. So if we just continue updating our model based on the new data, and so the new examples related to the new objects we see every day, we just learn about, distinguishes those new objects, and forget about the objects we had seen in the previous days. And you can also tell this from the evolving confusion matrix on the right, where these vertical bands indicate that the network is only guessing among the newest classes it has seen. So let's try to formalize a bit better deep continual learning. And let's say, I would say, would cover 90% of the deep continual learning papers in the last 10 years. So we can define a continual learning algorithm as possessing the following signature that you can see here in Formula 1, that is exposed to a set of experiences or tasks, if you will, that are containing a different data set for each of those. So you can see a representation of it on the image on the right, where for each experience you have a set of examples, for example, related to different classes. And then in order to evaluate those algorithms, we can also have for each experience a different test set to maintain our ability to control how good we are in terms of generalization capabilities, as we would do in standard machine learning. So let's assume that for each of those experiences or tasks, we have a training set and a test set. A continual learning algorithm, what would do is to start for every time step. So after seeing every, let's say, experience, is to start from the model computed the previous step and try to update it with the current training set. So the examples that we have access to, the observation we just collected from an environment, an eventual external memory when we can put examples from the past or specific assets we may need for our approach, and eventually having access to a task supervised signal, so an additional signal describing a change in distribution or a task we want to solve, a goal, whatever. Given all these, let's say, inputs, what we expect is to produce an updated mapping function, a parametric function f, our model, our predictive model, and eventually an updated external memory with that we can use later on. So this is the basic definition of a continual learning algorithm, and it is important to define its objective to understand what we're actually doing here, right? So the objective of almost any deep continual learning papers so far has been trying at the end of the day, so well, at the end of the stream of all these tasks, all these experiences, to maximize his predictive capabilities on each of them. So we are implicitly also assuming that the world is not changing, and those information that were useful in the first day, the first task, are still relevant, and we want to maintain them and incrementally adding new knowledge over time so that we can solve all those tasks and model of the distributions coherently at the end of the stream. And you can see this also explained, I mean, in this basic loss function, where what we want to maximize, well, minimize is the loss on each of the test set of those experiences, of those tasks. So the final objective of any learned, let's say, mapping function, neural network we're training is still the multitask, let's say, objective, right? We want to solve them all. And we added, to make it a bit more interesting, also a few desiderata, right? A few, desiderata connected to metrics, evaluation metrics that would push, let's say, to more desirable directions. For example, the idea that we should be limited in terms of memory and compute that we use with these algorithms. So we don't want, let's say, the memory to grow linearly with respect to all the examples of observation we have seen so far. We don't want the compute, especially, to grow even linearly with respect to the tasks or experiences we face, because these experiences may be also limited in terms of number. And we want to do it in a replay-free manner, for example. So it is quite understood that the brain does not store raw high-dimensional data to being able to learn continually over time. So many researchers are basing their investigations on neuroscience-inspired insights that would suggest we will go towards a replay-free approach, and so on and so forth. So trying to improve, let's say, these approaches we are developing in a more sustainable or attacking different scenarios where things are a bit more difficult, like lowering the amount of supervision, removing additional tasks, surrogates, supervised signals, etc. And also within our community, we have developed several approaches that is still difficult to categorize. They share a lot of things among each other, but I think it is convenient to still see a form of a fuzzy categorization with orthogonal, I would say, approaches to solve the problem. For example, regularization approaches, where we try to regulate learning while exposed to new data distribution, somehow preserving the information we acquired in the past and are relevant to model previous data distribution, and hence the parameters that are connected to those. Rehearsal approaches, where we allow ourselves to maintain an external memory where we store representative patterns data from the past, from which we can rehearse our knowledge while we learn about new data, new observations. Generative replay approaches, where we also maintain some form of compressed knowledge about the past in the form of models that can generate examples back from which we can rehearse with the same concepts, or architectural approaches where we isolate some parameters, we freed some others, or we add new parameters to make new space for new information. We can change the topology of the network, but those approaches are quite, I'll say, abstractly inspired by some evidence from biology as well. It is still interesting to know that if you want to develop like a concrete, practical continual learning approach, nowadays it's still useful to mix all of those different, even complementary approaches. So here, just for the sake of complete and also to help Antonio explaining, let's say, the second part of the talk, I will also go through a couple of those methodologies to make it more concrete. The basic one is experience replay, that is also well known in reinforcement learning. It's also known as just a replay approach in continual learning. But it is surprising still nowadays how good it is working even with a limited fixed external memory. So the amount of patterns and data that we need to store in order to refresh knowledge and to not forget is very, very limited with respect to the amount of data that we see over time. So, for example, in standard benchmarks is about 2% of the entire training set, if you consider all the training data encountered in a string. And also the approach is quite easy to implement, as you can see from the pseudocode on the right, where we just need to sample randomly, even in a basic approach. And there are 100 possible alternatives here, depending on the scenario you're tackling. So sample randomly from the current experience data, so the current data set we're processing, fill in your random memory till, let's say, you have reached the capacity, or we can also consider it growing, and eventually replace as well, about, let's say, a policy to replace examples randomly, for example, within the external memory once you reach the desired capacity. So with this completely random, let's say, approach, you can reach a very good performance in continual learning. So in case you don't know about this and you want to implement your own practical continual learning solution for a real world problem, I mean, the replay is one of the best first approaches you can design. And the second one that I wanted to explain, just to show a possible regularization approach, is elastic weight consolidation. You can ask Razvan more details about it, I guess. But it's a basic approach where you regularize learning while facing new observations, a new task. So if you assume to have like a trained neural network at the end of the first task and you encounter a new task, you can have like the standard LNU, let's say the loss related to that task, entropy loss, for example, for classification. And then you add the regularization term that somehow tries to disincentivate the change in the way that are relevant, the parameters that are relevant for the previous data distribution. So it is based on the strong assumption that is also quite empirically validated that parameters within a network don't share the same importance, right? So some parameters are very important, some others, maybe in a power law formulation, they are less important, they can be cut off. This is also known in pruning methodologies, for example. And so what we do to do this is just maintain a set of optimal weights computed at the end of the first task, and then see how far we are moving the current weight data case from these optimal values of the first task, and then trying to disincentivate this behavior with an importance value that we can compute in several ways. So if the weight is very important, we are not going to change it. If it is not that important, then we can change it. And well, the basic notion of the importance of a parameter with respect to distribution is given by the Fisher information, but it can be computed also in different ways that we have seen in continual learning being very useful and in practice. As for continual learning benchmarks and current scenarios we have been discussing, especially if you ask Guido van de Ven, it will give you like these three important scenarios that are very well known in deep continual learning that I wanted to present, especially for those of you that are not familiar with them. Task incremental scenarios, class incremental, and domain incremental. So in the task incremental scenarios, what we see for each experience, you recall we defined the problem continual learning from a stream of experiences, is to have a different task for each of those experiences. So here, the MNIST dataset, for example, can be split with the two classes for each class, and we would consider, let's say, a different classification problem for each of those tasks. So my master, I'm a robot, is asking me to distinguish 2 from 3s. Okay, I'm solving task 2. I'm given an image. Okay, and I say this is a 3 rather than a 2. So those are different detached tasks that I see over time and I need to solve. Then we have the class typical and very used class incremental learning scenario where we want to solve a unique classification problem, for example, trying to distinguish the 10 different digits of MNIST, but we see different samples coming from different sub-distributions over time. So we see all the examples of 0 and 1 first, then we see all the examples from 2 and 3, and so on and so forth, till the completion of the stream. So this is a clear sample selection bias, right? So the problem is fixed, the target function is fixed. We want to, at the end of the stream, a model is able to distinguish all these digits, but then we see just examples of the entire distribution we want to model over time. And then domain incremental, where we have a set of classes that are fixed over the different experiences or tasks. And what we see is a change in domain or in some latent variables related to the samples we collect. For example, we can consider this domain incremental problem of permuted MNIST, where we have a fixed permutation for each of those digits. And this means that we are trying to still solve the same unique 10-way classification problem, but we want to consider also these different distributions where the pixels are permuted. So for us, humans, it's very difficult to solve, as you can see here, the second task, but it has kind of the same complexity of the first. And we want to generalize over this set of possible 10 tasks, for example, 10 experiences. And so in deep continual learning, the current focus has been mostly starting from multitask scenarios, where we had just a couple, then a dozen of possible tasks with big number of examples for each task. Then we moved much more on class incremental learning problems, but still with this idea of using toy datasets, not that high dimensional, mostly focusing on supervised learning and on accuracy-related metrics. So the performance at the end of the stream were still the main focus for deep continual learning. Now we see a more recent trend growing towards this idea that maybe we don't need this concept of tasks after all. So we can solve just a task that is ever-changing in nature or is more difficult per se. We are working with more high-dimensional data streams with bigger data sets, etc. Tackling more natural streams that Antonio will discuss, and mostly within unsupervised reinforcement learning settings, and focusing finally on metrics that are very interesting, I think even more interesting for continual learning, which are scalability and efficiency. So we're not just trying to add a few percentage points at the end of the day for a particular benchmark. This is also why I think deep continual learning is difficult to understand for many people in our field. But more focusing on scalability, so how much we are growing in terms of our ability to understand the world, but still with fixed overheads in terms of memory and computational capabilities. So we really care about how those are growing, right? If we are considering an infinite set of experiences or observation we see over time. And just to give you an idea on how evaluation is conducted nowadays in deep continual learning, well, what you can see more or less in every paper is this plot on the left, possibly also with the descending curves, depending on what data set you are evaluating this, but essentially with the same idea that you want to measure the accuracy on a classification task, or if you have a performance measure, the main one. And then you compare with different baselines, for example, an offline approach or some naive approach where you just continue by propagation, or just a basic replay approach. And then I say, okay, yeah, AWC here in pink is better than other approaches in continual learning, not that effective as an upper bound of just retraining a model from scratch every time I see a new evidence, but still very much interesting in terms of accuracy. But what we are starting to develop as an interest from the community is not to look just at the accuracy at the end or in halfway through, let's say, this process, but also consider other dimension of the problem connected to other desiderata. For example, the ability to transfer knowledge that we acquired in a particular task in the future. So how better we are in learning new tasks where after we have learned about previous tasks, if you recall the futsal, soccer, 5-a-side, and then soccer 11 versus 11 example I made before, or how what we are learning later is impacting what we have learned before. So if after I have learned about soccer 11 versus 11, I'm better at futsal, at soccer 5-a-side. So all of these metrics can be computed also based on some, I would say, instantaneous, let's say, values here that they can compute while you're learning over the stream. So I didn't put it here, but in the gradient episode in memory paper by Ranzato, I think in 2017 or something like that, the standard backward transfer and forward transfer metrics were defined with this concept of evaluating the transferability of knowledge within the stream. You can see here the formulation based on these metrics maybe is worthwhile to go through. So what you do, instead of just collecting the accuracy after every step here, is to also see how a particular model after a particular experience is performing in the subset of each, if you recall, test set within the stream. So you can compute these R metrics after each of those training sets that you see over time, that you can see on the rows. And then after you have trained on that particular data set, you can test the capability of the model on each of the test sets of the stream. And you can, just add your accuracy within those metrics. So after you have computed these R metrics, all the different accuracy and backward transfer, forward transfer, all these, let's say, accuracy-related metrics to understand a bit better what's happening under the hood can be computed based on that. But essentially is what I have intuitively described before. So this concept of transferability of knowledge. And finally, you can also try to start measuring something else that is not related to accuracy. For example, how much your computational overhead is growing with respect to the number of experiences that you have faced. So we see that we are moving, let's say, from the left side to the right side as a community in terms of interest of what we should measure and how we should conduct comparisons between different approaches. But finally, just to conclude the same part of the tutorial and give the ball to Antonio after the break, I want to discuss also the focus in terms of really number of papers, approaches that we have been developing so far in deep continual learning. So here I did this game, I would say, because it's not that scientifically sound, of looking the number of hits on Google Scholar with respect to a particular combination of keywords. So you can see that for class incremental learning scenarios, we have a large number of papers, about 60% is with respect to the other numbers here. Then for task incremental, we have 900 hits, and for domain incremental, we have 543 hits. So I think this is quite reflective, at least from my perspective, of what what seems to be the focus of the community. Again, deep continual learning, not the entire lifelong learning community. About class incremental is maybe also in CoLLAs we can see those numbers, maybe you can have a confirmation, but a lot of researchers are focusing on class incremental. Then there is maybe a lot of researchers that are still using task incremental as their preferred benchmarks, but this is decreasing, I think, over time, because you tend to have negative reviews if you say that you have still task labels in your paper. And then domain incremental, which has even less papers on the topic, at least with these keywords. Then I put here 1% for the rest, but of course it's much bigger because there are hundreds of papers doing crazy things. But I see this, let's say, over focus, I would say, even on class incremental for a deep continual learning community. I wanted to convey this message today. We have also a paper that is trying to say, in short, that class incremental is not enough for continual learning. We should try to move, let's say, also towards other direction, not necessarily focusing on class incremental. And I try to say in this slide what are the pros and negatives of class incremental. So I think we started using class incremental because it's very easy to set up. So you can start from any static classification data sets, and you can create different splits and a stream based on those static data sets with a sufficient number of classes. For example, MNIST is split in 5 experiences with 2 classes. And it's very nice because it a bit exacerbate, I would say, catastrophic forgetting. So if you just continue naively to train your model on this set of experiences, you'll see that the overall accuracy is very low at the end of it. So it's very nice as a problem. It's easy to set up, and you can find new peculiar approaches that can solve it. And it is often depicted as one of the most difficult scenarios in continual learning. And I say that it depends on the metric you're using, right? So if you use forgetting, of course, it's the most difficult. And the problem is that, well, it's been fantastic to understand forgetting phenomenon and to find new ways to solve it. But we need to take into consideration also the negatives of it, right? So if we over-focus on this scenario is quite peculiar. It's a very specific setting in which we are saying we solve continual learning, and it is also quite unrealistic. So I invite you to think about possible real-world applications where class incremental is a useful problem. There are very limited number of applications where this is the case, because after all, what we want to do with class incremental is to find a way to improve our predictions on classes we will see in the future, right? Otherwise, why we are learning those classes after all? And if we see them, why should we not consider learning again from them and improve our ability to solve the task? So in this imaginary Venn diagram that I created, I tried also to represent how tiny it is the portion of class incremental with respect to what we can aim for in deep continual learning and lifelong learning in general. So with class incremental, we are focusing on virtual drifts, as we have described them at first, the first part of the tutorial, on sudden drifts. So you have this sudden change in distribution. We are focusing on classification, and we can add all these different constraints that class incremental is imposing, right? And we realize that this is a very little set of possible problems we are trying to tackle. And what I try to convey with Antonio in this tutorial is let's try to see what's outside, let's say, this little box of class incremental, and see what's here hidden by the question mark, essentially. So what we can do in continual learning will be very interesting and stimulating, and even useful for the community in terms of going beyond just catastrophic forgetting in class incremental learning. So that's the end of the first part of the tutorial. I hope I'm in time. I've not measured myself, but I just wanted to let you know, especially for newcomers, PhDs especially, that there is a 20 hours long course on YouTube that I created last year on deep continual learning. So if you want to learn the basics, you can check this out, and it's offered through ContinualAI, so course.continualai.org. And that in October, ContinualAI is also organizing an upcoming virtual conference completely for free. So in case you are interested, feel free to check this out. All right, thank you so much for your attention, and I guess we have the break.